Welcome to lecture number 5. Today we're going to discuss polarity in some more detail, and then also cover the intermolecular forces that we have to be considerate of for organic chemistry. So just a quick review of the polarity that we already covered. Looking at our first structure here, we should be able to remember that this bond between the carbon and the chlorine is polar because the chlorine is much more electronegative. So we can indicate that polarity with this dipole arrow, where we have the arrow pointing towards the more electronegative atom, in this case chlorine. This gives the chlorine a partial negative charge and the carbon a partial positive charge. And we can also consider the net or overall dipole moment for the molecule, which I'll draw in red, which will also be straight up to the chlorine because that's the only dipole that we have. Okay, what if we have multiple dipoles? We did touch on this last time. If we have multiple dipoles, such as in the second structure here, 1 and 2, if we have multiple dipoles, then the net or overall dipole in red would be the average of those dipoles, an average of those vector dipoles that we already drew. So if one is pointing straight up, one is pointing down to the right, then the net dipole is pointing right in between the two, from the carbon away from the carbon atom in between these two chlorines, because each chlorine is pulling electron density towards it, right? So the overall or the net dipole is simply the averaging of these two dipoles. Okay. I have here a picture of a tetrahedron. This hopefully is what you're envisioning when you see a tetrahedron. Remember, anytime I'm drawing structures like this, anytime we have 4 substituents around an atom, we need to envision those substituents as being at the vertices of this tetrahedron or triangular prism. So hopefully you're able to look at this tetrahedron and envision it anytime you see an atom with 4 bonds or 4 substituents around it. Remember, anytime you have 4 substituents around an atom, those will spread out as far as possible, which gives us the shape of a tetrahedron, right? So these 4 substituents, I'll circle in blue. 1, 2, 3, 4. It could be on this or on the right over here, either molecule. Anytime you have 4 substituents around an atom, they will spread out in the shape of a tetrahedron, okay? It's very important to remember that. We're going to look now at an example showing why that's important, okay? Let's consider the overall dipole of water. Okay, so if we draw water like this, like how we might have drawn it for our first lecture, it wouldn't make much sense if we draw dipole arrows to say that water has a dipole, because based on these 2 arrows, it looks like those vectors are canceling each other out. They're equal and opposite. But remember, this is not a true representation of a water molecule. This is why geometry is going to be very important for pretty much every chapter from here on out, because we have to be cognizant of the fact that molecules have 3 dimensions, okay? So a much more accurate way to draw this water molecule with some 3-dimensionality to it would be like this, right? Where we have some lone pairs. You can put the lone pairs sort of up here like this. envisioning that these four substituents are at the vertices of a triangular prism or a tetrahedron. Okay, so we could draw the water molecule like that. We could draw it like this. You can draw it at any orientation. You can draw the water molecule at whatever angle you prefer, but however you draw it, you will have the hydrogens oriented in this bent conformation. Remember, this would be a bent molecular geometry. However, if we consider the electron geometry, if we consider the lone pairs in addition to the hydrogens, we have tetrahedral electron geometry, because once again, we have 1, 2, 3, 4 substituents spread out around this oxygen atom, so they'll spread out in the shape of a tetrahedron. Okay? So now if we draw our dipole arrows, we have a dipole towards oxygen, we have a dipole towards oxygen, and now here's another concept we're going to introduce. We are also going to draw dipole arrows towards the lone pairs. Why? Because lone pairs, you can almost think of them as the most electronegative substituent you can have, because lone pairs are simply a pair of electrons, right? That's as electron rich as you could get, is a pair of electrons. Okay, so if you picture just a typical bond like this OH bond, there's 2 electrons in that bond. They're being shared. Oxygen does have a little bit more of a pull on those 2 electrons, but obviously if those 2 electrons were freed from hydrogen and simply acting as a lone pair, they would have much more electron density. Okay, so all things considered, we draw dipole arrows pointing towards the lone pairs. If we now consider all 4 of these dipole arrows, how would we draw a net or overall dipole? Well, it would be simply straight up in between all of these arrows, because the horizontal portions of all of these vectors are canceling each other out. We have 2 arrows pointing to the right, we have 2 arrows pointing to the left, but all 4 arrows are pointing up. Okay? If you haven't worked with vectors before, maybe that's a little bit confusing, but ultimately what we're doing here is we're simply averaging how all the arrows look on the molecule. Okay? We're simply taking an average of all these dipole arrows. In this case, the average of all of these would be pointing straight up. Okay? Let's see another example. Maybe it'll be more clear. Let's look at ammonia. We saw that last time, or a couple classes ago. So let's look at this example, NH3. Now we saw this before, but let's break it down into more detail. NH3 is trigonal pyramidal. The electron geometry is tetrahedral though, because we also have that lone pair. And again, here's the picture of the tetrahedron. We are going to envision this nitrogen as being in the center of that pyramid. Okay, this nitrogen is in the center of that pyramid. These 3 hydrogens are at the corners, the base, and the lone pairs at the tip. Okay. If we draw dipole arrows here, 1, 2, and 3, what's the net dipole of just these 3 arrows? It would be straight up. Straight up. It's the average of these 3 arrows or these 3 vectors. All of them are pointing upwards, and they're all pointing in towards each other. Okay, so their horizontal portions of these vectors will all cancel out, but they all have a vertical component. So the average of these 3 vectors would be straight up. We also have this vector pointing straight up to the lone pair, which is simply going to reinforce this red vector here that we already drew. So the overall dipole for NH3 is simply straight up like that, okay? So if the polarity concept and this overall dipole shenanigans confused you, I wouldn't worry too much about it. It's definitely a smaller topic. It's not entirely necessary for future content. So again, if it's going over your head now and after the workshop you still don't get it, that's okay. We're going to shift now into a more general talk of polarity with regard to molecules. We are going to classify them as being either nonpolar or polar. Now we could think of a polar molecule as being something that has an overall dipole. Generally speaking, it has some overall dipole in some direction, whereas the nonpolar typically does not have an overall dipole, or if it does, it's very weak. Now this is on a spectrum, okay? This is a spectrum. There's not a strict cutoff for considering something as being nonpolar or polar. And there is actually an index you can use to determine polar quantitatively. But for the purposes of this class, we don't have to consider that. We'll just generally call things either nonpolar or polar. If something is polar, it'll typically have some sort of overall dipole moment. Let's draw some examples here. Nonpolar, things that are nonpolar, hydrocarbons, any sort of hydrocarbon. I'll draw methane there as a Lewis structure, hexane, pentane, any sort of hydrocarbon is going to be nonpolar. Why? Because there's only CH bonds, right? A hydrocarbon by definition, if you remember, is something composed of hydrogen and carbon, okay? So any hydrocarbon will be a nonpolar molecule. Or we could have things like carbon tetrachloride, CCl4. I'll draw that over here. This, like the example we just saw previously, has dipoles in every direction away from carbon, which means that the overall dipole is 0. All these dipoles cancel each other out, okay? All 4 of these chlorines are pointing, remember, at the tips, at the vertices of a tetrahedron. So if you imagine dipole arrows pointing out and away in every direction like that, they simply cancel each other out. So there's no overall dipole for something like CCl4 or any symmetric molecule like this, okay? What are examples of polar molecules? Well, H2O would be a polar molecule. We saw the overall dipole for H2O just previously. Something like acetone, a 3-carbon chain with a C double bond O in the middle, because we have that nice big dipole pointing to the oxygen. Or it could be something as simple as ethanol, a 2-carbon chain with a OH, right? Something like ethanol. Just like water, we have an overall dipole here that's pointing straight up between the lone pairs, away from those 2 bonds, okay? So there's an overall dipole anytime we have an oxygen, such as in an alcohol like this. And there are many, many other polar solvents and polar molecules, but this should kind of give you an idea as to what you'll be looking for if you're asked to determine if something is polar or nonpolar, okay? Again, polar molecules will have some sort of overall dipole to them, some overall dipole moment. They'll have obviously polar covalent bonds in them. And our nonpolar molecules will be things like hydrocarbons, which are simply nonpolar bonds, or if there are polar bonds in something like carbon tetrachloride, they would be equal and opposite, cancel each other out to create an overall dipole moment of 0. So let's move now to intermolecular forces. So there are 3 intermolecular forces that we'll discuss, which are written here. So I like to think of polarity and intermolecular forces as sort of molecular stickiness or stickiness on a molecular level. These are going to be electrostatic interactions that we talk about, where we have partial positives, partial negatives attracting each other to sort of create that stickiness through electrostatic interaction. Okay, so you can sort of think of polarity and intermolecular forces as just molecular stickiness. Okay, that's at least how I like to think about it. So let's start by looking at dipole-dipole interactions. I'm going to draw an example right down here. Let's consider acetone. So this is a 3-carbon chain with a C double bond O. Now we know there's a dipole pointing up to oxygen, which makes oxygen partially negative, and this carbon down here partially positive, right? We have a dipole like this. So if we consider that if we have some sort of sample of acetone, we have billions and trillions of acetone molecules, right? We have many, many acetone molecules in just a single drop of acetone. Okay, that's another thing to be considerate of when we're talking about organic chemistry. We oftentimes just draw one molecule, but we have to remember that it's pretty much impossible to isolate one molecule of something, right? It's very difficult to do that. When we talk about acetone, when I draw the structure for acetone, we have to consider that there are trillions of these, okay? So in a solution of acetone, what could we envision happening if we have another molecule of acetone nearby, where we have this partially negative oxygen, this partially positive carbon? Well, we should be able to envision some sort of interaction. I'll draw with red, some sort of interaction or attractiveness between the partial positive and the partial negative, okay? The negative charge on this oxygen wants to be attracted to the positive charge on this carbon and vice versa. So what ends up happening is you get all of these acetone molecules sort of aligning themselves where they can properly interact with the respective charges that they're attracted to, right? Positive charges are attracted to negatives, negative charges are attracted to positives. So these molecules sort of get close to each other and arrange themselves in such a way that these charges become a little bit happier. So dipole-dipole interactions is simply when we get this electrostatic interaction, the attractiveness of other molecules, based on these dipoles that are present on the molecule, in this case on the C double bond O. Okay, so there's dipole-dipole interactions. Now let's talk about hydrogen bonding. Hydrogen bonding is sort of a classification of dipole-dipole interactions, where hydrogen bonding, we are specifically considering the dipoles between the OH bond, the NH bond, or the HF bond. Now in this class, it's really just going to be OH and NH. We are not going to see much of HF. We might see it as a reagent here or there. But in terms of hydrogen bonding, you should definitely be aware of the fact that OH and NH can hydrogen bond. So if we take a simple example like water, we have partially positive hydrogens, and we have a partially negative oxygen. Let's draw another water molecule right here. Okay, these partially positives are going to be attracted to the partially negative oxygen, and that partially negative oxygen will be attracted to the partially positive hydrogens. Okay, so we can draw as many molecules as we want. Let's draw another one here. That partially negative oxygen will be attracted to the partially positive, and the partially positive hydrogen will be attracted to that partially negative oxygen. Okay? So the hydrogen bonding is just like the dipole-dipole interactions, except it's specifically for the OH or the NH bonds. Okay? It's the dipole made from either a OH bond or NH bond, but it's the same idea where those partial charges attract each other. Okay, so there's hydrogen bonding. And the last one we have to consider is the fleeting dipole or the London dispersion forces. These are the smallest and typically the least impactful. I'll actually draw that right here. Typically the smallest force, whereas hydrogen bonding can typically be the most impactful or the largest. So in terms of the sheer strength of these forces, the fleeting dipole forces are the smallest. The hydrogen bonding forces are the largest. Okay, so the hydrogen bonding forces will have the most impact. Hydrogen bonding is actually one of the reasons why we have double helix DNA structures. There's a lot of hydrogen bonding present in the double helix, which owes to its shape. Another good thing to note here is that all molecules have fleeting dipoles. So every single molecule has some fleeting dipole. Let me draw an example of iodine, I2. Okay, so this is how we would typically see iodine, right? We have a bond between it. Each iodine has 3 lone pairs, okay? But instead of drawing it like that, I'm just going to draw sort of a cloud of electrons around these 2 atoms, where we have an iodine, and we have sort of a cloud of electrons around these. Right, because we have lone pairs all around them, we have the bond in between them, okay? So fleeting dipole simply means that if we have electrons, I will actually draw the electrons as maybe little red dots. These electrons can sort of be floating, in lots of different spots in and around these iodines. Fleeting dipole simply means that based on the random movement of electrons, you may have more red dots on the right side than on the left side at any given time, or vice versa. So we could have more red dots over here, we could have more red dots over here, or it could be very equal, and we could have them spread out very evenly, okay? So fleeting dipole is simply the random movement of electrons. It's the creation of a very slightly partial positive or partial negative just based on the random motion of electrons. Okay, so every single molecule, to some degree, has fleeting dipole forces. Okay. And again, fleeting dipole is the smallest force. It does not have much of an impact. Hydrogen bonding is going to be the most impactful. And hopefully we can understand now that if we have a lot of intermolecular forces, if we have a lot of polarity, this is going to alter the physical properties of a molecule. Let's write that down here. These forces will affect the physical properties of molecules. Okay, examples of this could be boiling point, melting point. Okay, this is what you'll typically see. There are other physical properties that are affected as well, but let's just take a look at these for now. Let's now consider these two molecules I have drawn off to the right. We have on the left here isobutylene, and on the right we have acetone. Note that the only difference here is what's at the end of this double bond. In one case it's a carbon, in the other case it's oxygen. So let's just consider the forces at play here. A fleeting dipole. Of course, these both have fleeting dipoles because all molecules have fleeting dipoles. Okay, so they both have some fleeting dipole. What about dipole-dipole? Isobutylene on the left has no polar molecules in it, so there's no dipoles for us to consider. But on the right here, we do have a dipole. We have a dipole towards oxygen, which gives oxygen a partial negative, and it gives this carbon a partial positive. And what about hydrogen bonding? In this case, we don't have any OH or NH bonds, so neither one has hydrogen bonding. So the only difference between these two molecules is this oxygen and this carbon. That oxygen creates a dipole. That oxygen creates a dipole, which gives us these dipole-dipole interactions. Now we have a partial negative. Now we have a partial positive. All of a sudden, it's like we created a little magnet, a little molecular magnet. Now all these molecules are sort of sticking together. They have more attractive forces. So what would happen to the boiling point? Why don't you try to think about that? What would happen to the boiling point? Which one should be higher? Which one should be lower? The boiling point of isobutylene is about -7 degrees Celsius. If we consider the molecule on the right, it has dipole-dipole interactions. It has more molecular stickiness. You can think about it that way. The boiling point is going to be higher. The boiling point is going to be around 56 in this case. You don't have to know the exact numbers. These numbers are just to show you that just by switching out a carbon for an oxygen, you create these dipole-dipole interactions that sort of increases the stickiness or the attractive forces of this molecule. All of a sudden, this molecule over here, the acetone, is much more attracted to other molecules like it, other molecules that have this dipole. And so the boiling point is now increased because of those strong intermolecular forces keeping things together. Okay, hopefully that makes sense to you. This is one reason why H2O has such a high boiling point relative to other liquids that are similar to it, because we have a dipole, right? We have dipole-dipole interactions, specifically hydrogen bonding. This is a very strong force, and we have this partially positive, partially negative with the OH bond. So water molecules really hold on to each other very tightly. So the boiling point for water is quite high. Obviously, we know the boiling point for water is 100 degrees Celsius. Okay. So as we increase the amount of molecular forces, let's actually write that right down here in this little box here. If we increase the intermolecular forces, that's going to give us an increase in boiling point or melting point. Okay. If we increase the amount of intermolecular forces, we're going to have an increase in boiling point or melting point, right? And thinking about it qualitatively makes sense because as we increase the number of interactions, we increase that molecular stickiness, the attractive forces. Those molecules are going to be less likely to separate into a liquid or separate into a gas. Okay? Okay, let's now talk a little bit about what else could influence those physical properties. Okay, so let's just look very simply at a couple molecules here. Okay, we have a 4-carbon chain, we have a 5-carbon chain, and we have a 6-carbon chain. This is butane, pentane, and hexane. And their respective boiling points will be 0 degrees, 36 degrees, and 69 degrees. This is very straightforward to understand. As we increase molecular size, as we increase molecular weight, we increase the boiling point. Why? Because as we increase the size, we have an increase in the London dispersion forces or the fleeting dipole forces. Okay? So as we increase size, we increase the London dispersion forces, we increase the molecular stickiness, and those molecules will have a higher boiling point or a higher melting point. Okay? So an increase in molecular size or mass will give us an increase in boiling point or melting point. Okay, and that's pretty straightforward, that's pretty intuitive. If you have a very large molecule, it's more likely to be a solid at room temperature. It's going to have a higher boiling point, a higher melting point. If you have a very small molecule, it's more likely to be a gas. It's going to have a much lower boiling point. And then the final consideration we have to make is branching. What would branching do to our intermolecular forces? Let's consider a few structures here. We have a 5-carbon chain, pentane, and what we're going to do now is just branch it off a little bit more each time. Okay, so we have a 5-carbon straight chain, a pentane, in the first structure. And then here we have a butane, a 4-carbon chain with a methyl group coming off of the second carbon. And then in the very last case, we have a 3-carbon chain with 2 methyl groups coming off. So you should be able to picture here, we have a straight chain, we have some branching, and now we have a lot of branching. Okay, so as we increase our branching in our structure, we're going to change the intermolecular forces. Let's look at these boiling points. 36 degrees for the straight chain, 28 degrees for some branching, and down to 10 degrees with a lot of branching. So what's the consideration here? We have to understand, we have to be considerate of the surface area. Let's think about the surface area. When we have a straight chain, we have a lot of surface area. As we condense this with branching, the surface area becomes smaller and smaller. If we have less surface area, we are going to have less of an impact from those London dispersion forces. Okay? So as we increase the branching, we are going to decrease the London dispersion forces, which will give us a decrease in boiling point or melting point. Okay. So again, as we increase the number of branches we have, as we increase our branching, we are going to decrease the amount of London dispersion forces at play because we are decreasing the surface area of our molecule. We're decreasing the total area that it's taking up. So this is going to decrease the melting point or the boiling point. Okay. Now the final thing that we'll talk about is solubility. And this is very straightforward. If we just think about our nonpolar and our polar molecules, let's just write this here. For solubility, likes dissolve likes, right? We've already talked about that before, or I'm sure you've seen that before, rather, maybe in high school chemistry. So this means that nonpolar molecules will likely dissolve other nonpolar molecules, and polar molecules will dissolve polar molecules. So let's take a polar molecule here, like acetic acid. So the acetic acid molecule is very polar. We have several dipoles on this molecule, right? We have lots of oxygens, we have OH, we have hydrogen bonding. This is a very polar molecule. So it's going to dissolve readily in a polar solvent like H2O. Let's take a very nonpolar molecule like hexane. This is very nonpolar because it has no dipole. This will readily dissolve in any sort of oil or other nonpolar liquid. Okay. So we have some polar molecules up top here. We have some nonpolar below, and these are just two examples. But this is just to remind you that likes dissolve likes, polar molecules dissolve in polar solvents, and nonpolar molecules dissolve in nonpolar solvents. Okay. This is sort of the basis behind soaps, by the way. Soaps, you saponify an ester. You also might see it called a hydrolysis process. And so soaps typically have a polar functional group on one side, and then an extremely long chain of carbons on the other. So we sort of have this polar group on one end, and then we have a very non-polar group on the other end. So soaps have the ability to combine both polar things and non-polar things, okay, because they have both a polar section and a non-polar section on them. Okay, so we'll just do one quick practice problem here. There will be much more in the workshop, but let's just consider intermolecular forces and what it might do to boiling point. I'm going to draw two molecules in each case, and we're just going to circle the one that has a higher boiling point, and I'll just discuss as we go. Looking at these two molecules, same molecular formula, different structure, so these would be considered what? Constitutional isomers or structural isomers. Which one's going to have a higher boiling point? I actually think I gave this in the very first lecture. So hopefully you remember that OH should have a higher boiling point because this one on the left has hydrogen bonding. Remember, hydrogen bonding is a very strong intermolecular force. So if you see hydrogen bonding, that's going to play a big role. Both of these have dipoles, right? They both have CO bonds. But the one on the left has the OH bond, and that OH bond is particularly potent, which is why we call it a hydrogen bond. That's going to really increase that molecular stickiness and keep that as a liquid. So the higher boiling point will be the OH, will be the alcohol. Okay, what if we have these here? Which one has the higher boiling point? Well, remember, as we increase our branching, we decrease the amount of intermolecular forces we have. So the higher boiling point is going to be the more linear structure, which is the one on the left. We'll have more surface area, which gives us more London dispersion forces, which gives us a higher boiling point. And then finally, what about this one? Which one has a higher boiling point? Well, the one on the right has a higher boiling point because it has a much higher molecular weight, higher mass, and again, it also has a higher surface area. So we are simply going to have more London dispersion forces, more of a fleeting dipole, which is going to give us a higher boiling point. Okay. We'll do more practice problems in the workshop, of course, but these are just some to get us started. Okay, that's all I have for lecture 5, and I will see you guys for workshop 2.